VSX, a tale of two stacking technologies. In the world of network engineering, high availability is king. We need our networks to stay online, even when a device fails. Aruba offers two powerful technologies to achieve this: Virtual Switching Framework, or VSF, and Virtual Switching Extension, or VSX. While both aim to create a resilient network, they operate quite differently. Think of VSF as stacking. It combines multiple physical switches into a single logical switch. This new logical switch has one control plane and one management plane. You manage the entire stack as if it were a single device, which honestly really simplifies administration and configuration tasks for network teams. VSF is a traditional stacking technology. It is designed for simplicity and ease of use, particularly in the access layer of a network. When you connect several switches using VSF, they elect a master switch. This master handles all the control plane functions, like routing protocols and spanning tree protocol calculations. The other switches in the stack act as members, forwarding traffic under the master's direction. If the master switch fails, another member is quickly elected to take over, ensuring the network continues to function. This process provides redundancy, but keeps the management straightforward. On the other hand, VSX is a more advanced virtualization technology. It is a form of multi-chassis link aggregation, or MC-lag. With VSX, two separate switches are paired together. Unlike VSF, each switch maintains its own independent control plane. This is a critical distinction. They synchronize specific control information between them, but they operate as two individual devices that appear as a single logical device to other network components. This dual control plane architecture eliminates a single point of failure at the control level, offering a higher degree of resilience, making it ideal for the core or aggregation layers of a network. The primary benefit of VSX's dual control plane is its ability to perform live software upgrades without network downtime. Since each switch in the VSX pair runs its own control plane, you can update one switch while the other continues to forward traffic uninterruptedly. Once the first switch is updated and back online, you can update the second one. This capability is known as in-service software upgrade, or issue. VSF, with its single control plane, cannot perform this kind of hitless upgrade. If you update a VSF stack, the entire logical switch must reboot, causing a brief but noticeable network outage. The Aruba 6200 and 6300 series switches are workhorses designed primarily for the network access layer. This is where end-user devices like computers, phones, and IoT devices connect. For this role, VSF is an excellent fit. It allows network administrators to manage an entire wiring closet full of switches as a single entity. For example, you could stack up to 8 Aruba 6200F switches, or up to 10 Aruba 6300F or 6300 Menoker switches. This drastically reduces the number of devices you need to configure, monitor, and troubleshoot, saving significant time and effort for the IT department. The 6300M in particular benefits greatly from VSF. As a modular switch, it offers flexibility in port types and power supplies. By stacking multiple 6300M units, you can create a highly dense and resilient access layer block. Imagine having nearly 500 ports all managed from a single command line interface or a single IP address. This really simplifies tasks like VLAN configuration and port security. When you need to add a new VLAN, you configure it once on the VSF stack master, and the configuration is automatically pushed to all member switches. This consistency helps prevent common human errors. VSF technology on these switches uses standard network ports for stacking, which adds to their flexibility. You do not need proprietary stacking modules or special cables. You can use standard direct attach copper cables or transceivers with fiber optic cables to connect the switches in the stack. This makes it easy to stack switches that are in the same rack or even in different racks within the same wiring closet. The Aruba 6200 and 6300 series leverage this simplicity to provide a cost-effective and powerful solution for building scalable and easy-to-manage access networks for campuses and branch offices. The inherent redundancy of VSF is also a key feature for the access layer. If one switch in the stack fails, the other switches continue to operate. The VSF link, which carries both data and control traffic between the members, ensures that traffic can be rerouted around the failed unit. While there is a brief interruption as the stack reconverges and a new master is elected, the downtime is minimal and often acceptable for the access layer. For most end-user applications, this level of resiliency is more than sufficient, providing a great balance between performance, cost, and availability, which is exactly what the 6200 and 6300 series are designed to deliver. A common question that arises is whether a switch like the Aruba 6300M, which supports VSF, can be upgraded to support VSX through a firmware update. The answer is no, and the reasons are rooted deep in the hardware design of the switch. VSX is not just a software feature. It is a system-level architecture that requires specific hardware capabilities. The technology relies on a constant, high-speed synchronization of control plane information between the two switches in the VSX pair. This synchronization needs a dedicated, low-latency path that is separate from the standard data forwarding paths. The hardware designed for VSX, such as the Aruba 8300 or 9300 series switches, includes specialized components to facilitate this synchronization. They have what is called an inter-switch link, or ISL, which is established over high-speed ports. More importantly, the underlying application-specific integrated circuits, or ASICs, and system architecture are built to handle the dual control plane operation. This includes the ability to keep control planes independent while sharing state information seamlessly. The ASICs in the 6300M are optimized for access layer functions and VSF stacking, not for the demands of running a completely separate, yet synchronized, control plane. Think of it like trying to make a family car perform like a Formula One race car, just by changing its engine oil. The entire chassis, suspension, and engine of the race car are purpose-built for extreme performance. Similarly, the 6300M's hardware is purpose-built for its role as an access layer switch. It lacks the internal hardware pathways and processing power required to manage the constant state synchronization that VSX demands. A firmware update can only unlock capabilities that the hardware can support. Since the foundational hardware for VSX is absent in the 6300M, no software update can add this functionality. This design choice is intentional. Aruba engineers its products for specific roles within the network to optimize performance and cost. The 6300M is engineered to be an excellent, cost-effective VSF-capable access switch. Adding the hardware needed for VSX would increase its cost and complexity unnecessarily for its intended use case. By creating different product lines for different network layers, like the 6300 series for access and the 8300 series for aggregation or core, Aruba ensures that customers get the right features and performance for the right price without paying for capabilities they do not need. Even without VSX, you can still achieve a highly resilient, active-active uplink configuration using a VSF stack of Aruba 6300M switches. The key here is to use link aggregation groups, or LAGs. A LAG bundles multiple physical links into a single logical link, which increases bandwidth and provides redundancy. Since the VSF stack acts as a single logical switch, you can actually create a lag that spans across multiple physical switches within that stack. This is a pretty powerful feature that gives you both link and device redundancy in your uplinks to the core or aggregation layer. Now, here's a practical, step-by-step approach. First, physically connect your 6300M switches together using the designated VSF link ports to form the stack. Once the stack is formed and the master is elected, you can go ahead with the uplink configuration. Let's say you have a VSF stack made up of two 6300M switches. You would connect one uplink cable from the first switch to your core switch and a second uplink cable from the second switch to that same core switch. On the 6300M VSF stack, you configure these two physical ports as members of a single LAG. On the upstream device, which might be a VSX pair of core switches, you'd also configure the corresponding ports as members of a lag. This creates a single, high-bandwidth, logical connection between your entire 6300 M-access stack and the core. The Link Aggregation Control Protocol, or LACP, will manage the links, making sure that traffic is distributed across both physical uplinks. This means you're using the full bandwidth of both links at the same time. So, an active-active setup. If one of the uplink cables gets disconnected or a port fails, LACP automatically redirects all traffic to the remaining active link. Furthermore, if an entire 6300M switch within the VSF stack fails, the uplink connected to it will go down, but the uplink from the other stack member stays active. Traffic will seamlessly fail over to the surviving link and switch. This configuration really provides excellent resiliency for an access layer deployment. It protects against uplink cable failure, uplink port failure, and even the failure of an entire switch within the stack. By leveraging VSF and standard lags, you can build a robust and high-performing access layer with the 6300M series without needing the more complex VSX architecture at this layer. When your network requirements demand the highest level of availability, such as for a data center or campus core, you really need to step up to a true VSX architecture. This means selecting hardware that is specifically designed for it. The Aruba CX 8300, 9300, and 10000 series switches are the primary platforms that support VSX. These switches are built for the aggregation and core layers of the network, where uptime is absolutely critical. They've got the necessary hardware and processing power to maintain two independent control planes while synchronizing state information for a seamless failover experience. To implement VSX, you start with two identical VSX-capable switches. For example, you might choose a pair of Aruba 8325 switches for your campus core. The configuration involves establishing the inter-switch link, or ISL, between them. The ISL is a lag, typically using two or more high-speed ports, like 40 gig or 100 gig, that carries synchronization traffic and also serves as a data path if a downstream link fails. You then configure the VSX parameters on each switch, defining their roles and a keep-alive mechanism. The keep-alive uses a separate path, often a dedicated management port, to monitor the health of the peer switch. Once the VSX pair is established, they present a single logical device to the rest of the network. Any downstream switch, such as a 6300M VSF stack, can connect to the VSX pair using a standard lag. This is the beauty of VSX. It's totally transparent to other devices. The downstream switch believes it's connecting to a single, highly resilient chassis. This multi-chassis lag, or MC lag, is the foundation of a VSX design, allowing for active forwarding paths, load balancing, and hitless failover if one of the core switches goes down for maintenance or fails unexpectedly. If your network has grown and you now need VSX capabilities, but you already have 6300M switches, the best strategy is repositioning. The 6300M switches are still extremely valuable as high-performance access layer devices. You can purchase a pair of VSX-capable switches, like the 8325s, to serve as your new aggregation or core layer. Your existing 6300M VSF stacks can then connect upstream to this new VSX pair using the active-active laggy configuration we just talked about. This tiered approach really aligns with best practice network design, placing hardware with the right capabilities at the appropriate layer of the network, and ensuring stability, performance, and scalability.